Welcome back, everyone. Today, we're taking a seriously fascinating journey into the universe's ultimate mystery. But before we even get started, I want you to just stop and consider this for a second. Right now, drifting completely silently through our very own Milky Way galaxy, there are estimated to be tens of millions of rogue, entirely invisible objects. And they have gravitational pulls that are so intense, they literally warp the fabric of reality around them. I am incredibly excited to guide you through this explainer today because we're going to dive deep into the physics, the sheer scale, and the mind-bending reality of the darkest entities known to science.
Okay, let's dive into this, because to really grasp what we're dealing with, we kind of have to throw our everyday intuition right out the window. These cosmic phenomena are completely invisible to the human eye, right? Yet they possess such unimaginably powerful gravitational grips that they actually dictate the motion of entire star systems. But it's not just about a strong physical pull. Thanks to Albert Einstein's theory of general relativity, we know that gravity isn't just some invisible tether. It is a literal warping of spacetime. These objects distort the cosmic fabric so severely that the fundamental rules of reality are just stretched to their absolute breaking point. So, you might be wondering, how does something this extreme even come into existence in the first place?
Well, it actually starts with an epic cosmic battle, one that's been raging for millions of years inside a massive star. You see, a star is essentially this incredibly delicate balancing act. You have the immense, crushing weight of gravity constantly pushing inward, and that is perfectly balanced by the outward pressure of nuclear fusion burning away at the star's core. But that balance only holds up as long as the fuel does. For stars that exceed a very specific mass threshold, which is known as the Chandrasekhar limit, running out of fuel means an instant and catastrophic loss for fusion. In a fraction of a second, that outward pressure just vanishes. Gravity violently wins, crashing down on the star's core. The outer layers are blasted away in the spectacular supernova, while the core itself collapses into an unbelievably dense, infinitely crushed remnant. And just like that, a black hole is born.
And this brilliantly illustrates the sheer, mind-boggling scale of what we're dealing with when we categorize these objects. What we just described creates what's called a stellar mass black hole, which is usually a few times the mass of our sun. Now, quick aside, contrary to popular belief, these things are not cosmic vacuum cleaners. If you were to magically replace our sun with a black hole of the exact same mass, Earth wouldn't get sucked in. We'd actually just continue orbiting completely normally. I mean, we'd freeze, but our orbit would be fine. But then we have the true monsters of the cosmos, supermassive black holes. And we're not talking a few times heavier than our sun here. We're talking about millions or even billions of times the sun's mass, all packed into a single, localized region of space.
And these supermassive giants aren't just rogue wanderers. They're essentially the anchors of the cosmos. They sit right at the center of nearly every large galaxy in the universe. And yep, that includes our very own galactic neighborhood. Roughly 26,000 light-years from exactly where you're sitting right now, Sagittarius A star, which is a supermassive black hole about 4 million times the mass of our sun, is holding court at the very center of the Milky Way. And this actually presents one of the greatest chicken or the egg debates in modern astrophysics. Did the supermassive black hole form first and then pull the galaxy around it? Or did the galaxy form first, eventually creating a hyperdense core that collapsed into the black hole? We're still trying to figure that out.
Now, since they are entirely invisible and emit absolutely no light themselves, you're probably wondering how on Earth we actually track them down. Well, the answer is we look at their dinner plates. When gas and stardust get caught in that gravitational pull, they don't just fall straight down. They spiral inward at incredible speeds, forming this massive, swirling structure called an accretion disk. The extreme gravitational friction and twisting magnetic fields in that disk heat the plasma up to millions of degrees. When they're feeding voraciously, they can power quasars, which paradoxically makes these dark objects the single brightest beacons in the entire universe. Add in these enormous jets of plasma shooting out from the poles at near light speed, and you realize that we actually find the invisible by looking for the most violent cosmic fireworks imaginable.
So, the crucial point is understanding where the observable universe actually ends. That boundary is called the event horizon, and it's mathematically defined by what astrophysicists call the Schwarzschild radius. It's really all about escape velocity. So to escape Earth's gravity, a rocket has to travel about 11 kilometers per second. But as you get closer and closer to a black hole, the required escape velocity climbs higher and higher. The event horizon is the exact perimeter where the required escape velocity hits 299,792 kilometers per second. That is the speed of light. And since absolutely nothing in the universe can travel faster than light, nothing can escape once it crosses that line.
It is the ultimate point of no return. But actually crossing it, that's a wildly different experience depending on your perspective. Just imagine you're floating in a spacecraft right outside this boundary. To your friends watching from a safe distance, Einstein's time dilation dictates that you would appear to slow down and eventually freeze in time forever at the edge, slowly fading to red. But for you, you wouldn't even notice a bump as you crossed over. However, as you fall closer to the center, the tidal forces take over. The gravity pulling at your feet would become exponentially stronger than the gravity pulling at your head. You would literally be stretched out into a long, single string of atoms. It's a genuinely gruesome but fascinating physical process that astrophysicists actually officially call spaghettification.
So, what happens to all that spaghettified matter once it's actually pulled inside? Well, it travels down the gravitational well to a location known as the Singularity. This is where all the mass the black hole has ever consumed is crushed into a point of zero volume and infinite density. Let that sink in. And right here is where our current scientific models just throw their hands up in defeat. Because to understand the singularity, we need to combine general relativity, which is the physics of the macroscopic, super-heavy universe, with quantum mechanics, the physics of the microscopic, subatomic world. And right now, those two frameworks just absolutely refuse to play nicely together. The math simply breaks down into infinities, meaning the true nature of a black hole's interior remains one of the greatest unsolved mysteries in all of science.
And that brings us to a really vital shift in how we should perceive these enigmatic giants. Black holes are not merely cosmic destroyers. They are laboratories for exploring the deepest laws of nature. It is so easy to just think of them as these terrifying cosmic threats, but they are incredibly useful test engines for the universe. Today, observatories like LIGO are literally detecting gravitational waves. These are actual ripples in spacetime caused by black holes colliding billions of light years away. These colossal impacts allow us to test Einstein's theories in the most extreme chaotic environments possible. So they don't just destroy, they actually reveal the absolute limits of our reality.
So, I want to leave you with this to ponder. If humanity eventually developed the technology capable of safely traversing the cosmos to observe the edge of a black hole right up to the event horizon, would you volunteer for the mission? Would you risk it, knowing that you might witness phenomena no human has ever seen, even if it meant risking a slip past the point of no return? Think about your own curiosity in the face of the universe's ultimate mystery. And that wraps up our explainer on black holes for today. Make sure you join me next time because we're going to be zooming out even further to explore something even grander, the ultimate fate of the universe itself. See you then.